So hi, everybody. Joyce and I are going to go through the software for simulating a light field camera. Light field cameras came up in the lectures, and there were a number of questions about that. And so I thought it'd be fun to just put together a little script that shows you how it is we simulate light field cameras. This script is a little more complicated than what you already have seen, but I include it. It includes other repositories that build on ISET3d, and I include it here just to get you motivated. Maybe some of you will want to do some testing and evaluation in some of your projects related to light field cameras because there was so much interest in it. So we thought we'd go through it. So let me share my screen so you will see the code. And I have put, I'm going to put this in a repository ISET3d, but I'll copy it for if anyone asks me. I'll show you where the ISET3d tutorials are and how it is we simulate these cameras. And ISET3d is the extra repository that we use beyond ISET-CAM. And also I should say ISET-Lens. You'll see come up in a moment. We add this repository to ISET-CAM. And you always have JSON.io. It's in there. You may not have noticed it yet, but we always have that in there. Anyway, the outline for what we're going to do today is we're going to initialize this stuff. We're going to make some 3D scenes. We're going to simulate a light field camera, and I'm going to show you what it all looks like in the hope that it makes sense for you. So the first little bit of this, to do these simulations, we initialize. You've seen this all the time. We initialize ISET-CAM. We check that Docker is on your computer. You need that. You need to have the ISET-Lens repository and ISET3d on your path, and that just gets initialized here. Then when you have those on your path, we have these methods for importing and creating different 3D scenes. And this particular scene that I just read in here is we call the rendering information necessary to make a 3D scene. It's recipe, and it knows things about the camera, which we're about to fully define now, and about how to render things and so forth. And these are places where it sticks the files as it does the rendering. So I ran that, and then here is the code to go and build the taking lens, the imaging lens, and I'm just showing that to you here. The lens that's going to be at the front of the camera has got this first surface curving, and here's one element and then another element. This is a double Gauss form. This is the aperture. Light comes through. The lenses often have glass here on the front end, glass on the other, an aperture in the middle. These are the units, millimeters up and down and so forth. And so that's this particular one here. Again, I just keep showing it to you. So that's this one. And then we're going to go make ourselves a micro lens. So we did the same thing. The micro lens is much simpler. The micro lens is what's going to sit on front of the image surface, the sensor surface. There's going to be a lot of these micro lenses. This is just an example of one, but we're going to set its size and the relative density of these things. So how am I doing, Joyce? Is that all?
Okay. Yeah. So you need the Docker container because you're going to be using PBRT.
Yes.
And then all of these things that you're doing for setting up the lens is using code that's in ISET3d.
Thanks for saying that. For setting up the lens is actually using the code that's in ISET-Lens.
Oh, okay.
Yeah, but that's right. But it's also available through ISET3d, but it's basically we have a lot of little lens information in lens creation and so forth in ISET-Lens. And this is a pretty standard lens, the double Gauss lens. This one has got a focal length of about 10 millimeters. And this little micro lens here is really, really tiny. Notice, I don't know if let me make it bigger. You can see it's really small. This is in millimeters, and this thing here, when it first comes up, has this 10 to the minus third millimeters. So you're kind of looking at microns over here in terms of how big this thing is. So it's a really small little lens we're going to put on top of the sensor surface. Then we need to assemble to tell the rendering algorithm, the PBRT, what to do. We need to assemble the taking lens, which I showed you up here, and a whole bunch of these micro lenses. There's going to be thousands of these little micro lenses. We need to tell PBRT, yeah, you got all these lenses in your path. And we build that into a lens file. We use actually the same Docker container to go create the whole lens file that defines both the main lens and the whole array of micro lenses. And the basic geometry, what they look like, just to remind everybody about these kinds of cameras. The blue circles here are showing you the positions of every one of the micro lenses. And these are about 12 microns across. And then the squares are the pixels that are behind the micro lens. So this micro lens has an array of pixels. It's about 5 by 5. This one's got an array of pixels 5 by 5 and so forth. And when we do the calculations with the light field camera, we're going to do something like pick out this pixel, so let's say the center one, and show you an image from that. Or we'll pick out, this pixel at the edge and its partner over here and its partner, show you an image over that. That would be called the sub-aperture views. This one, all those will be one. There'll be another one over here and so forth. So there are and different ways of assembling these pixels will let us do different things that's kind of the purpose of the light field camera. So this is just a little reminder about the fact that there's micro lenses and then pixels sampling underneath them.
And the pixel position tells you about the direction of the ray, right?
Exactly. Each pixel is receiving from this aperture, from this micro lens aperture, but which rays it gets it codes by its position the angle at which the light is coming in from the taking lens, from the bigger lens. So that's right, what you just said. Okay, so that was through here. And now this part here is we're using the kind of coding that we use in with this recipe in ISET3d. We built this combined lens and give it a name of this lens, and we print out a little information about it, and then we create a camera that has that lens. And this is the way in ISET3d we create cameras. Pi for PBRT to ISET pi camera create, and we're creating a particular type of camera. We're setting its focus distance. We're setting its the size of the film or sensor that we're going to be simulating. We're telling you about the resolution, and so forth. I should have said that all the little numbers about how many micro lenses there are. I set this up to be 40 times 8, 320 micro lenses in the horizontal and vertical directions. So it's going to be, the images are going to be 320 by 320. The total film height as well. Okay, how many micro lenses do you have times the micro lens height? How many pixels are we going to have per micro lens? Well, we're going to have 5 by 5 because I just set that here. So all that was just set, and that was used to go make this little picture over here. So that's the camera. We set its properties, its resolution, and so forth. We set the aperture diameter of the lens. We could do that, and then I just wanted to make sure that I could summarize everything, and so that's shown over here as just a little summary of where everything is and the different properties of it. That's what this summarizes. Okay, and then the next step is I wrote that thing out. I wrote the camera out and the name of the scene that we're going to render and everything. And then I just called the render command. And that render command ends up producing a ISET irradiance image. And remember, it's an irradiance image because it's after the lens. It's the light that's come from the scene through the taking lens, and in fact all the way through the micro lenses. And I'm just going to zoom in here a little bit, just so you get a bit of it. Even maybe at this resolution, as I zoom in, you can see that there are all these little circular things here. I'm just going to keep going. And in each one of these little circles, that's the irradiance. This is a description of the irradiance that's about to fall on the sensor underneath. The reason there are all these little circles here is because that's underneath a particular microlens. So one microlens, the next microlens, the next microlens, and so forth. And so there's 320 microlenses in each dimension. Each one has 5 pixels. So if you look at how many rows and columns a sensor has, it's samples we're going to have, it's 5 times 320. So that's going to be 1,600 pixels that we need for the sensor. And this is under one microlens, under the next microlens, and so forth. And each one of these is a irradiance, is a spectral irradiance. And that's, the whole image that we're simulating right there. Okay.
So you figured out the sampling so that each of those points falls on a pixel. But you could oversample too, right? Where you might have more.
When we set up, I'm not exactly sure I got your question, but I set up how many microlenses there are going to be.
Right.
320 by 320. And I set up how many pixels there were going to be underneath each one of them. It's going to be 5 by 5. And everything else kind of flows from that. Okay. So therefore, what's the film height? Well, the film height is calculated, tell me the microlens height and how many there are. That's how much film I need. Okay. What's the film resolution? Well, tell me the film height divided by the pixel size, and that's the and that's the resolution. So that's what we created here.
Okay. Yeah. So basically it was film resolution that.
Yeah.
Okay.
That's right. That set that up. Okay. So that provided us with the optical image. And I think it's kind of fun to just to pull them out, even at the optical image stage, pull out the subaperture views. So, here's the whole, we've got 1,600 pixels, but we just rearrange them here in this view so that if you pull out the pixel at the center of each microlens, and assemble them into a picture. And this picture, ask yourself how big is this picture going to be? How many samples in this picture? 3 by 3.
You're asking me?
Actually, yeah, I'm telling you. 320 by 320.
Yeah, it's the number of, the center pixel.
That's right.
It's the number of microlenses you have, right?
Exactly.
Okay.
It's the number of microlenses. I got 1 pixel from below.
Every microlens, which is in the center of each microlens. Okay.
This one is in the center of each microlens.
I see.
This one is the one just to the right.
Right. So this is something you assembled from the optical image.
We assembled, and the code for assembling it was really just, it's a little function. And I should give a shout out to a former postdoc from Gordon's group, but now he's a professor in Australia, named Don Dansereau. He wrote a really nice set of collection routines for handling various calculations with light fields. I haven't checked it in the last couple of years. He might have updated it, but we use it we use his format to go, take the optical image data and go turn it into these subaperture views and so forth. And so Don did a nice job on that. And one of the projects that I can imagine somebody wanting to do is just do more and more with Don's toolbox on these kinds of rendered images, refocus and do various things. And so shout out to Don. If he ever sees this, I hope you're well, Don. Okay, so then that was the optical image. So now we have in ISET-CAM, when you know a lot about the optical image, you kind of you can create a sensor that's spatially matched to that optical image. It has
just one point though.
Sure.
The last thing you showed was not the optical image. It was taken from the optical image to assemble the aperture images, right?
Yes.
Okay, so now when we go to the sensor, we're going to be operating on that image. Okay.
So let me dwell on that. Yes, let me dwell on that. This is the actual optical image right here. And each one of these little circles that we were looking at before, if I pull one pixel out of the center of each one of these, that would be the center image right there.
See, that would be the light that would be falling, that you would predict would fall on the center of the pixel.
And that's right.
In the sensor.
That's right.
Okay.
And so now we're going to make and just you said, we're now going to make a sensor that sees this image, and it's going to have one pixel at every position here, at the same sampling resolution. We're just going to match its sampling resolution. It'll be 1600 by 1600. It's going to pick up every one of those little pieces that are in the optical image here. And that's what this code does. It creates a sensor, and then it computes, with that sensor, it computes from the optical image what the response of the sensor would be. And then we bring it up in a sensor window. And that, shouldn't be terribly surprising either. Just kind of looks like that. I'm going to make it just a little easier to see by changing the rendering. I don't know if that helped or not. But you can see, sensors actually have red, green, and blue pixels, have color filters in front of them. So in fact, at this point, here we have the whole irradiance. Here we have an R, G, or B pixel at every point. So we're going to have to do something to start thinking about integrating all the different sensor properties. But again, it's 1600 by 1600 because that's how we designed it, and it picks up every little point over here. It's the same basic image, and we're now going to take that image and we're going to process it using basically. We're going to process it the way we process all kinds of images. We're going to demosaic it and just render it into color balance it, do all the things that we normally do to an image, and render it into an image processed form. And that's what that looks like. So here it's now been. This is the light field now after it's been demosaicked and interpolated and so forth. And, you can see this part is in good focus. This part is a little blurry. That's the depth of field. The stuff far away is blurred, so forth. An opportunity is to use the light field data to set the focus. So to put this in good focus, or this in good focus, or the far in good focus. That's, we can do a certain amount of that. And I'm going to leave that as an interesting, somebody who wanted to do that for a course project, make sure that how well it worked on this image and several other test images. That's a entirely reasonable course project.
I have a question, Brian. So before you showed the optical image is a representation at every wavelength. So you have an image for every wavelength that you're sampling. And then you generated this aperture, the aperture images, and presumably that would also have a representation for every wavelength. So when you could now generate a similar image for the processed one. And you always do that, generating that aperture image after you demosaic?
Yes.
Okay.
In fact, that is what I'm going to do right now.
Okay.
Just what you said. So here, at this point, we've lost our wavelength information. And I was just supporting your point that here, when we're in the optical image, if I go and I look at some little piece, it's got wavelength information. Here's wavelength, and here's irradiance and so forth. So this is still a spectral image. But by the time you get to the sensor image, this is not a spectral image. This is now an image in terms of electrons or volts at the sensor. So we've lost the wavelength information when we go from the optical image into the sensor image. And we're kind of getting to the end of this. So now I'm going to take that image processed thing. I'm going to tell it, how many micro lenses did you have, and what color space are we operating in? And I'm going to go get this light field. And so now this light field is like all of these images here, except it's from the camera. And I'm going to show it to you in a slightly different way. I'm just going to copy that command and paste it into the buffer here. And it'll bring up a little video player that shows you the different subaperture images in a sequence, as if you're just kind of moving around in a circle in that subaperture. And so what you're seeing is, as it moves round and round, you're seeing that it's like you're looking at the scene from slightly different points of view, right? Each one of these images that comes up here is that same 320 by 320, but they're showing you, the subaperture views sometimes from the right side of the pixels and under the micro lens, sometimes on the left, sometimes at the top, sometimes at the bottom, just circling around. And for that reason, I wanted to give you the sense that these images are like looking at the scene from ever so slightly different points of view. Each one of the subpixel apertures is a view of this. And the other thing, you can see this weird purple stuff that's floating around there. That's an indicator that, as you move off to the edge of the micro lens, not every subaperture view is actually that good. Some of them are noisy. Not that much light gets there, or if light gets there, it mostly simulates one compared to the other type of sun, the red versus the green versus the blue. So we're kind of looking at a little video showing the subapertures individually, and that, in a way, is the information that we have to work with to go and create all the modified views, the refocused views or depth estimates and so forth. It's like having this little collection of images. And you can see, therefore, why people think that a light field camera, building it this way, is fine. You get all these subaperture views of seeing the world from slightly different points of view. If you had decided to build a little array of cameras, just one camera to the next on the outside, each one a separate camera, a little 5x5 array of cameras, you would also have views like that. Each camera would give you a little 5x5 array of cameras, that is each 320 by 320, would also give you subaperture views like this. Just the baseline spacing would be different. It would be the center of the camera to the center of the camera instead of the pixel spacing in the micro lens. And it wouldn't be an integrated package, and you'd have to do a lot of other stuff to make it go. But in any event, these are the subaperture views. The point of this is you can see the relative, like this rook over here, its position with respect to the thing in the far background is changing, or the position of this pawn and that pawn and the bishop over here. Everything is just sort of moving back and forth as you pull out the different subaperture views.
And why does the center piece not move?
Well, that's
geometry, I guess. It's hard for me to.
Well, it is kind of. I'm not sure that I should even try to answer that. I'm not.
But it falls out of the geometry.
Right now, it's not moving in this image, but its position relative to that position is changing.
Right.
This thing's position relative to that.
Right. Right. Okay, and then all the swirling colors there, that's noise. Basically, those are pixels that don't get enough light, and then the image processor amplifies it, so it looks that way, right?
That's right. And in building a real device, you need to
remove the noise, I guess, and interpolate or something.
You need to deal with that issue. The light underneath the micro lens it's got some shading artifacts, and that can lead to color problems and so forth. You need to think about that if you're building a real device. But this simulation gives you all the different pieces. So let me just remind you of all the different things that we went through, right? We went through, setting up the compute environment with the different repositories. We took a 3D model of a PBRT of a chess set. We defined taking lens, big imaging lens over here. We defined the micro lens arrays and all their properties. We figured out, what the geometry, we selected how many micro lenses there were and how many pixels underneath each micro lens. And we then went and rendered the optical image, which, as you pointed out, is a spectral irradiance image. So it literally is, the whole thing. And then that gave us the optical irradiance. It gave us the sensor image, and we then converted that into the image processed one as well. And so there are the data, and then we used Don Dansereau's toolkit to go and segment out the sub-aperture views and look at things and see things from different points of view. And so all that's possible to do in simulation, and to try different sizes and different lenses and different demosaicing algorithms and so forth. And it's possible for anyone who has an interest in light field cameras and doing experiments with them. This is one way forward.
Cool. Does Don's package have routines in there for estimating depth, recovery depth from them?
It does. And yeah, thanks for saying that. It's got, for example, I stuck one example down here for refocusing. And got all kinds of different routines in there for different things. And I haven't studied it closely, and it's been on my bucket list of things that, what are the algorithms and what has Don gotten there, and contributing back to Don's work. For all I know, by the way, he has a newer update to this package. Last I looked at it was a couple of years ago. I just snagged it from him. But there could be more to it at this point.
So people could play around with the number of pixels underneath the micro lens, see how well that, how much information that gives you for autofocusing, and also, for changing focus, and also for estimating depth. I guess you could play around with the exposure duration to see the effect of noise.
That's true.
And then the lens design, yeah.
Distance between the micro lens and the sensor, the size of the micro lens, the curvature of the micro lens.
Yeah, and the nice thing about this is that you have, because of you're using PBRT, you have depth information, so you actually know the real depth. So you could do the recovered depth and real depth.
Yeah,
you can't really do with a real light field camera, because you don't really have a good quantitative estimate of the depth. You don't have a ground truth, in other words.
Right.
So simulation allows you.
What you're saying is important. Because this is a simulated environment, you do know the actual depth. You couldn't simulate a light field camera without knowing.
Sure.
So you do have that information, and if you wanted to explore depth recovery from light field data,
you could do it quantitatively.
Because you know the ground truth of the depth. And
cool.
Yeah.
Cool. Do you know if anybody's ever used machine learning as well? Because you have ground truth, right?
That's true.
Yeah. Anyway, very interesting. Thanks.
Okay, thank you, Joyce. Let's I'll stop the share, say thank you. And
bye-bye. Thanks.